Hello everyone, and welcome to Physics 270, where we learn to appreciate and to love physics. I hope you are all doing great today and are excited for another great lecture, this time on gravitation. So chapter 13 is the next chapter we're going to be talking about. We're done with chapter 12. Last time we discussed how objects stretch and shear and can be compressed. And moving on, we will be talking about gravitation, chapter 13. And then the final chapter we will be looking at is chapter number 14. That will be next week. But I'd like to get started today with a quote by none other than Isaac Newton, who said, "Genius is patience." And of course he would say that. Legend has it that he had this epiphany while he was sitting under a tree, just relaxing under a tree. An apple fell, hit him in the head, and that's when he realized how gravity works. That's when he thought of the law of universal gravitation, which is exactly what we will be studying today. But I hope that you too, as you sit at home and relax, I hope you are struck in the head by some kind of object, hopefully not lethally, but have all kinds of inspiration as to how things in this universe work. Okay, so we've discussed translations, we've discussed rotations, we've discussed deformations, we've seen how a bunch of different forces work. We've looked at the friction force, the spring force, and today we're going to be talking about a very special force. We're going to be talking more generally about how things move due to the gravitational force. So we've looked a little bit at the force of gravity already. Remember, we've discussed that if we've looked at, let's say, some kind of box, and we said if this box has a mass m, then on the surface of the Earth, it has a force that points, it experiences a force that points towards the center of the Earth, which is typically what we call down. And so that's the direction of the force, but we also discussed the magnitude of that force on the surface of the Earth, again, is equal to m times g, where g we until now had be this constant 9.8 meters per second squared. Now, the gravitational force is very, very special compared to other forces, because that force, so let's look at Newton's second law, which says that when you consider the sum of the forces acting on an object, the sum of the forces should equal the mass of the object times the acceleration of the object, and that includes the direction as well. But and we've discussed various forces that you can find here on the left-hand side, but gravity is the only force that we know that on this left-hand side, so the Fg, is the only force whose magnitude is proportional to the mass. So Fg equals mg. And we noticed that that had to be the case because the acceleration of an object is an object which only experiences the gravitational force is independent of its mass. So if I plug in the force here on the left-hand side, the gravitational force, and that's the only force acting, then I find that from Newton's second law, I get mg is equal to ma. These m's cancel, and you find that the acceleration of the object is independent of its mass. Okay, so we wanted it to be that way because we noticed that, let's say, a brick and a feather in vacuum, when there's no resistive forces, when the gravitational force is the only force acting, they accelerate downwards due to the gravitational force of the Earth at the same rate, with the same acceleration. But gravity is also very special because it is a fundamental force. Okay, what does that mean? It means that we do not understand it in terms of other forces. So a counterexample is the spring force. So the spring force is not a fundamental force. You can ask, well, okay, why does the spring exert a force? And we can start to answer that question. We can say, well, the spring is actually made out of these molecules, and the molecules have various bonds, experience various forces amongst one another, and they can be flexible, and they can push and pull on each other, and that's what's called the Miller force. And then you can ask, well, but why do the molecules behave that way? And then you can say, well, the molecules are made out of atoms, and they have these charged nuclei, and there's these things called electrons that are kind of surrounding them, and these electrons can pull and push on each other, and the reason that the molecules have these bonds and interactions is because the stuff that they're made out of sort of interact in this way. And you can then ask, well, why do atoms and electrons interact in this way? And then you can say, well, because of the electromagnetic force. So we know that there is this electromagnetic force between charged particles, and we can describe sort of the behavior between those due to that force the best we can. And then you can say, well, why do objects experience the electromagnetic force? And that's kind of where you can't answer, and you say, well, the electromagnetic force is a fundamental force. In other words, I'm not able to understand it or to explain it in terms of these other forces. And so gravity is very similar in that way. We are not able to explain gravity in terms of some deeper force. It just seems like all objects that have mass or energy kind of interact with each other gravitationally. So these two things, the magnitude being proportional to the mass, and the gravitational force being a fundamental force, make gravity a pretty special force, and in my opinion, worth studying. So we've talked about this mg being the magnitude of the gravitational force so far, but I want to describe to you in depth the law of gravitation as Newton described it. And so to understand more generally what the force between two objects is, you have the law of universal gravitation, which says that every two particles will each, with a mass, at least as far as we will go into, every two particles will attract each other with a force that is proportional to the product of their masses. So these two objects will cause a force on each other. That force will be attractive in nature, and the magnitude of the force between those two particles is going to be proportional to their masses. So if this has mass m1, this has mass m2, there's a gravitational force that is going to be proportional to m1 times m2, and it is going to be inversely proportional to the square of the distance between them. So if these two particles find themselves a distance of r away from each other, let's just call it r, then the gravitational force is proportional to m1 times m2, and then it's inversely proportional to r squared, meaning that if you were to double the distance between the particles, the gravitational force would be smaller by a factor of 4. So if r goes to 2r, r squared goes to 4r squared, which means that the gravitational force is reduced by a factor of 4 when you double the distance. If you double one of the masses, the gravitational force doubles. If you double both of the masses, the gravitational force quadruples. You'll notice here that we expect the left-hand side, the force, to have units of newtons. And on this right-hand side, I have kilograms times kilograms divided by meters squared, which just goes to show that the units don't match up here. And in fact, there is a constant of proportionality. As far as we can tell from experiments, it is constant. And that constant we will denote by big G, or G sub n. This will be, G is Newton's constant. And experimentally, we can verify that in SI unit, so you can find what units this has. It should have newtons divided by kilograms squared times meters squared. So the way I got that is I just solved for G. I bring over the masses and the r squared. G should have units of newtons times meters squared divided by kilograms squared. And from experiment, we can figure out what the magnitude of G is. And in SI units, G has a magnitude of 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. Okay, so this equation over here describes the magnitude of the gravitational force. Of course, the force is a vector, and I already told you the direction of this force vector. It will always, if you only have two particles, or for any two particles, the gravitational force between them will always be an attractive force. So the force on this particle, the gravitational force the gravitational force on this particle due to that particle points towards the other particle. And so we can use an r hat vector. So I can write that the vector here is the r hat vector, where by r hat I just mean the unit vector in the direction in which the other particle is located. Okay, so the gravitational force is always attractive. The gravitational force due to another particle always points towards that other particle. But I want to address this maybe seeming contradiction, which is that so far the gravitational force was just m times g. And so this g was a constant, and over here it looks like, well, okay, you have an m, maybe that m is the same as that m, but then you also have this g m2 over r squared, and this r squared changes as your location changes. And so was I lying to you this whole time when I was saying that the force of gravity due to the Earth at the Earth's surface is this thing over here, where g has a magnitude of 9.8 meters per second squared? And the answer is, in a sense, yes, but not exactly. I wasn't exactly lying. So I want to explain to you why it's kind of okay to make that approximation. And so I'd like to show to you, I'd like to derive why it's okay to sometimes say that that the force of gravity is just mg when you're referring to objects at the surface of the Earth. And so let's look at the situation. Let's look at kind of the bigger picture here. The bigger picture is that this is the Earth, and you have some object sitting right there, which is approximately at the surface of the Earth. And so if we just take the Earth to approximately be this point particle located right there at its center, which would have a mass of m sub Earth, and then you consider some other particle out there, let's just call it m1, some object that we might consider on the surface of the Earth, and that is located at an approximate distance equal to the radius of the Earth, r sub e. In other words, you pretty much have two particles, one separated by approximately the distance that is equal to the radius of the Earth. One has a mass m1, the other has a mass m of the Earth. You would expect the gravitational force here, to be attractive, as we said, of course, but you would also expect the magnitude to be equal to g times m1 times me divided by re squared. So this is the distance squared, the product of the masses, and Newton's constant. And so we are wondering whether this is approximately equal to m1 times g, where g is 9.8 meters per second squared. So I have my m1 over here. I'd like to pull that out right there. And the question is, does g times mass of the Earth divided by r squared approximately equal 9.8 meters per second squared? Now you can check that the units work out, and they do. And so let me just give you here the mass of the Earth, or let me just start with the radius of the Earth, about 6.37 times 10 to the 6 meters. That's the radius of the Earth, and you also have the mass of the Earth is about 5.972 times 10 to the 24 kilograms. We can plug in. Remember, G is 6.67 times 10 to the negative 11 in SI units. And so if you multiply G times the mass of the Earth and divide that by the radius squared, you should maybe pause this video and calculate that, plug it into your calculator. You'll find that indeed this is approximately equal to, so G ME over R Earth squared is approximately equal to 9.81 meters per second squared. So it's okay to say that the gravitational force is approximately equal to M1 times G, where G is 9.81 meters per second squared, if, and only if, you're talking about an object that is at the surface of the Earth. Notice that if your distance from the center of the Earth were to be doubled, if you were out here, then your gravitational force would not equal M1 times G. It would equal M1 times this G times the mass of the Earth divided by the total distance squared. Okay, so I wasn't completely lying to you. We made a simplification, but now we're going back and more explicitly stating what the gravitational force is. I'd like to kind of summarize what we've said so far and kind of put it in a new light that is hopefully going to help you understand the difference between what we call a field, a gravitational field or an electric field. And we won't get too much into that in this course, but when you take electromagnetism, this will hopefully prove useful. So we've really described two things. We've said that a particle of mass m, when placed in a gravitational field, will experience a force, and that gravitational field has a magnitude and a direction, and that field we will call G, little g, just like the G we've had so far. If a particle of mass m finds itself in a gravitational field G, then it will experience a gravitational force which is equal to m times G. So the magnitude of the force is determined by the magnitude of G and the magnitude of m, but I am no longer going to assume that this little g over here is 9.8. More generally, this G, this gravitational field, depends on the object that has created the field. So this is the first thing that we realized. The first thing that we realized is if you place an object of mass m in a gravitational field, it experiences a force. Masses in fields experience forces. But there's a second lesson to be learned here. And that second lesson is that an object of mass m, so let's consider this object over here, maybe it's the Earth, whatever it is, an object of mass m creates, at a given point, it also creates a field. Okay? And so the gravitational field created by an object of mass m is equal to G times m divided by the distance between the object and the point of interest. So if you want to know what the magnitude of the gravitational field is right there, you just have to look at the distance here and the mass. And so the field has a magnitude that is equal to Gm over r squared. And so if you combine these two rules, and then you look at two particles, okay? Here's one particle, M1, here's another particle, M2. Let's consider the gravitational field that is created by M2 at the location of M1. At the location of M1, M2 creates a gravitational field, G M2 over r squared. This distance here is r. if we would like to know the force experienced by M1 due to the gravitational field created at that location by M2, all we have to do is take that gravitational field and multiply it by M1. So the gravitational force experienced by 1 due to 2 is g m1 m2 over r squared. So this is the universal law of gravitation, and I have sort of broken it down into two pieces here. One that says that masses experience forces when they are in fields, and the other says that masses create fields around them. Notice that there is a symmetry here in that the force experienced by 2 due to 1 is going to equal m2 times the gravitational field created at 2 due to 1. And that, of course, is g m1 over r squared. And you'll notice that these two expressions are the same. Notice that these forces are equal in magnitude, but opposite in direction. This force points to the right. That force points to the left. The forces are attractive. And these forces also are Newton's third law pairs, right? So this is equal and opposite in direction to that force right there. So particles in fields experience forces. Particles create around them gravitational fields. So let's start exploring the extent to which we've understood this stuff so far. So let's do quick quiz 13.1. Quick quiz 13.1 says that there is a planet and there are 2 moons around this planet. And the 2 moons have equal mass. The 2 moons have equal mass. Moon 1 is in a circular orbit of radius r. So let's start to draw this. That's the Earth. Here's Moon 1. It has mass m, radius r. And Moon 2 is again in a circular orbit, but of radius 2r. So that's r. That's 2r. So Moon 2 is circling around in a greater orbit, but it also has mass m. So the 2 moons have the same mass, different radius of going around the Earth. The question is, what is the magnitude of the gravitational force exerted by the planet on Moon 2? Is it 4 times as large as the force on Moon 1? Is it twice as large? Is it the same? Is it half as large? Or is it a quarter of the force on Moon 1? So let's consider the force on Moon 1 by the Earth. The force on Moon 1 by the Earth is going to be g m of the Earth times m divided by r squared. And let's consider the force by the Earth on 2. The force on the Earth, the force on the second moon by the Earth, I guess it's just symmetric, is going to be equal to g, mass of the Earth. They have the same mass m, but now instead of dividing by r squared, r becomes 2r. So F2 is going to be 4 times r squared. And notice that the force experienced by the second moon is 4 times less than the force experienced by the first moon, and therefore the correct answer is that the gravitational force exerted by the planet on Moon 2 is 1/4 as large as that on Moon 1. Okay, so this was just a qualitative understanding of how the gravitational force scales. Let's do this example 13.1, which will have us do some calculations and explicitly use the this force law that we just learned about. So example 13.1 on page 390 says that 3 billiard balls, each of mass, so this is example 13.1, the masses of the billiard balls are 0.3 kilograms, so the mass is 0.3 kilograms. So that's the mass of the billiard balls. The 3 billiard balls are placed on a table at the corners of our right triangle as shown. Okay, so here's the situation. Here's one billiard ball, then there's another one, and then there's another one. The 3 billiard balls are a distance A, B, and C from each other. We are told that A has a magnitude of 0.4 meters, B has a magnitude of 0.3 meters, and C has a magnitude, of course, of 0.5 meters. We are to calculate the gravitational force vector on the cue ball, which is this one down here, M1. So this M1, they want to know what is the gravitational force vector on this ball, in the lower left corner, resulting from the other 2 balls. And they also want to know the magnitude and direction of this force. So we have to find the force vector, then find the magnitude of that vector, and find the direction of that vector. Now, a very common mistake is for people to think, okay, this object is experiencing a force. The force experienced by this object is going to be m times some field due to the other 2, but that's not what this problem is asking about. So you don't want to start computing the force experienced by this vector, by this mass. All you want to do, all you're asked, is find the force experienced by this mass. So according to the universal law of gravitation, the force Fg experienced by that mass is going to be m1, that's the mass, times the g at that location. Okay? So that's one way to look at it. Another way to look at it is that the total gravitational force, and this is going to be equivalent to that, the total gravitational force on the mass right there is going to be the sum of the gravitational forces acting due to this object on that object and due to that object on that object. So in other words, I can say that the gravitational force vector on mass 1 is going to equal, let's just call it F of, let's see which one is 1 and which one is 2. They call this M2 and this is M3. So it's going to be M13 plus the force of 1, 2. Okay, so as long as I can express these vectors, now notice that F13 is going to point in that direction. It is a force that points towards the other particle, and F12 is going to be this other force that points in that direction towards that particle. So in other words, I have to add these 2 vectors that are perpendicular to each other. My F13 is in the x direction, my F12 is in the y direction. I think the book, that's how the book does it. Let's try to consider what F13 is. F13 is going to have a magnitude of G M1 M3 divided by R squared, where this R is equal to B. Right? It's the distance between 1 and 3. That's 0.3 meters. I have 0.3 kilograms times 0.3 kilograms divided by 0.3 meters squared. So in SI units, that's all going to cancel and just give you G. And therefore, and I can't forget that this points in the I hat direction or X hat direction equivalently. So this is a force This here is a force that has a magnitude of 6.67 times 10 to the negative 11 newtons and points in the x direction. You can do something similar for F12. You can say F12 should just be G times M1 times M2, both of which are 0.3. And then we want to now divide by the square of this distance, which is A, which is 0.4 meters squared. You want to plug that all in, and you find that this was 6.67 times 10 to the negative 11. That's going to be 3.75 times 10 to the negative 11. But crucially, this force here points in the j hat, or y hat direction. So the force vector on object 1 is simply the sum of these two forces. Y hat and j hat direction don't mix, so you just write it out as this force is going to have a j hat component and an I hat component, and that is just the force vector. If you then want to find the magnitude of that vector, you take the square of this and add it to the square of that, and then take the square root. That would give you the magnitude of this force vector, right? So this is this, that would give you, that would be the magnitude of the combined vector. And then if you want to know the direction over here, you'd say that the tangent of this angle theta should be equal to the y component divided by the x component. So you can therefore take the arc tangent to find, so you take the inverse tangent to find what theta is. Okay, so that is example 13.1. I'd like to do one more example before we quit. Let's do example 13.2, which is on page 392. So this one is kind of cool because it will allow us to calculate the average density of the Earth, which I think is pretty interesting, the fact that we can do that although we're just at the surface of the Earth. So this is, let me just write it out, example 13.2, this is on page 392. So using the known radius of the Earth, so RE, I told you what that is earlier, and it is known. And using also the fact that G is 9.8 meters per second squared at the surface of the Earth, find the average density of the Earth. So the average density of the Earth, so the average density of the Earth right here is going to, of course, be the mass of the Earth divided by the volume of the Earth. So the mass of the Earth divided by the volume of the Earth. And now we know that the volume of the Earth can be approximated as the volume of a sphere. So the volume of the Earth we can approximate as the volume of a sphere, which is 4/3 times pi times the radius of the Earth cubed. And the radius of the Earth, we assume, is given in this situation. But we have to figure out a way to approximate the mass of the Earth only using the fact that G is 9.8 meters per second squared. And we know, of course, that G, as we calculated at the beginning of the lecture, G should equal G times the mass of the Earth divided by the radius of the Earth squared. So this should equal, and does equal, G, which is 9.8. But using this relationship over here, we can solve for the mass of the Earth, and we can write out the mass of the Earth should be G times the radius of the Earth squared divided by Newton's constant, which we know to be 6.67 times 10 to the negative 11. And so from here, we can use this to calculate the density of the Earth. The density of the Earth should be this GRE squared over the Newton's constant divided by the volume of the Earth, 4/3 of pi r Earth cubed. And so going through this calculation, you find that the average density of the Earth, so if you just plug in all the numbers that we have here, you find that the average density of the Earth is 5.5 times 10 to the 3 kilograms per cubic meter. Okay, that's the density of the Earth. Kind of interesting that we calculated it. We were able to calculate it. But there's a second part to the problem that says, what if you were told that a typical density of granite at the Earth's surface is 2.75 times 10 to the 3 kilograms per meter cubed? So 2.75 times 10 to the 3 kilogram per meter cubed. So the stuff that the surface of the Earth is made out of is not as dense as the average density that that we computed, that we calculated. In fact, it's about half the density that we calculated. And so from this, we can conclude that whatever makes up the core of the Earth must have a density that is much greater, much higher than the average value. So if all the stuff that we see around us has this much lower density, half as much as the density as the average, that means that the stuff that is at the core must have a density that is higher than the average density. And so I think that it's pretty interesting that by doing these kinds of experiments on the Earth, calculating if you get what g Newton is, the gravitational constant, if you can measure the radius of the Earth, then you're able to understand something about what the center or the inner core of the Earth is made out of. So with that, I hope you enjoyed this lecture on how a simple free fall can actually lead to some more complicated ideas. We will continue working on this stuff next time. And I look forward to talking to you soon. Take care.